Hello, everybody, and welcome to another wonderful day of physical chemistry. So, today we finally get to that wonderful topic of an actual system to study. So, we're going to be trying to focus all of our knowledge of operators and wave functions on actually a fairly simple system, and that's the free particle. So, this can be anything as a nice escaped electron, an electron gun, a neutron emitter, a free photon. Doesn't really matter what the system is. If I'm just essentially a particle moving through a vacuum, this is going to be how I behave. So, not too surprisingly, this is going to be our simplest system to study. And from here, we're going to essentially keep adding in perturbations to develop real complex systems. So, we're going to start by looking at the free particle. So the free particle is essentially defined as having a potential energy of zero. So no matter where we are in space, potential energy just doesn't matter. So not too surprisingly, we're going to make the system more complicated by essentially playing around with that potential energy term. But for now, all we have is kinetic energy. And we happen to know the kinetic energy operator. Again, negative h bar squared over 2m, second derivative with respect to position. And again, you'll notice we're just doing a free particle in one dimension. So just moving along in the x direction, essentially back and forth, straight line in a vacuum. That's about as simple as it can get. So we've already demonstrated one potential eigenfunction for this Hamiltonian. That's essentially cosine kx. And it is worth noting that, yes, this is an unnormalized wave function. And when dealing with a free particle, pretty much all of our wave functions will be unnormalized, which hopefully makes sense because otherwise this would be 1 over infinity because we're spread out over infinity when dealing with a free particle. So we're going to ignore the normalization constant because we're spread out all over heaven, and I mean that literally. So we're just going to focus in on the main portion here. So cosine kx, we're again, as we've demonstrated before, k is going to be related to the de Broglie wavelength. This is going to have an associated energy of k squared over h bar squared over 2m. And not too surprisingly, this means we can analyze the system pretty nicely in Dirac notation, where again, we apply our Hamiltonian to our operator, then integrate, gives us k squared 8 over h bar squared over 2m. Again, just gives us back our kinetic energy. So this is actually fairly straightforward as we've already solved most of the difficult bits. We're just putting in our notation. However, part of the trick is that it turns out I might not just want to know the energy of the system. I might want to know other properties. Simple one is I might want to know the momentum of this wave function. So I can determine the momentum of this wave function by applying our momentum operator, again, h bar squared, or h bar over I, first derivative. And now we run into a little bit of a problem because when I take the first derivative of cosine kx, I get negative k sine x. Turns out cosine kx, while it's an eigenfunction of energy, isn't an eigenfunction of momentum. So now we have a slight problem we have to deal with. So one of the ways we can deal with this is by realizing that cosine kx can be expressed as a combination of two values that are eigenfunctions of momentum, and that's exponentials of imaginary numbers. So again, using Euler's formula, we can rephrase cosine kx as 1/2 of the sum of e to the ikx and e to the negative ikx. So let's go ahead and try and apply our momentum operator to this more complex system. So I can try and figure out the total momentum of this free particle by trying to apply the momentum operator to each part. So 1/2 of e to the ikx and 1/2 of e to the negative ikx. So when I go ahead and do that to the positive portion, well, I end up generating ik h bar over I2. So again, I2 ik comes from the derivative, and then h bar already was there. So this simplifies to kh bar over 2, or again, as a reminder, k is going to be related to the de Broglie wavelength. But this actually gives us the momentum of the system. We have a positive momentum of kh bar, because again, that's what isn't present in the wave function. So when I go from here to here, kh bar pops out. So momentum of positive kh bar works out great. Now let's do it to the other part. So not too surprisingly, this is going to give me the same answer, but negative. So now I have two different momentum answers. So the momentum of this part is kh bar, and the momentum of this part is negative kh bar. So what we can do is try and rephrase it. This is how we determine the total momentum of the system, but is again by applying the momentum operator to both of these parts collectively, which again is going to be the same as adding these two components. So what we end up getting out is, again, positive kh bar, negative kh bar. I can now pull out these kh bars and leave behind 1/2 e to the ikx plus e to the negative ikx. Wait a minute, this is just cosine kx. So all I'm left with now, when I apply the momentum operator, is kh bar minus kh bar. Another way to think about this is by applying a momentum operator or any operator to a wave function. If I'm able to break this wave function down into the constituent eigenfunctions of my operator, then my ending eigenvalue, quote unquote, is going to be simply the sum of the eigenvalues of each part. So in this case, kh bar minus kh bar, well, that's 0. Turns out that a free particle with this wave function has a momentum of 0. And the reason why actually can be expressed fairly nicely. I have equal amounts positive motion and negative motion. So my particle is equally moving forwards and backwards. So the net movement is nothing. The particle is constantly moving, but it's moving equally forwards and backwards, so it ends up staying put. And this is a very common feature of the movement of particles. We actually tend to find a lot of particles that are fairly stationary, but they're less stationary because they're not moving, and they're more stationary because they're moving back and forth equally. They're pacers. They don't stand, they pace. And this is a good way to try and look at a lot of our systems. So this is essentially the simplest form of essentially a wave function being described as a superposition of different eigenfunctions. And we're going to dive a little bit more generally into this idea of superpositions next time. Till then, take care.